I'm going to have one person join me. Thanks.
Morning. Morning, Professor.
You're in a class by yourself, buddy. You ever been told that?
Oh, yeah.
Yeah.
No, never
Well,
happened.
now it's happened. It's happened. You're in a class by yourself. All right. We're going to get started here on electrochemical stoichiometry. Now, the situation that we're kind of taking advantage of here has to do with the tingle displacement reactions and how one element can be more active than another. Now, there was a situation back when you were doing probably intro to chem and then in general chemistry where you looked at single displacement reactions, you probably saw an activity table that allowed you to determine if one element was more active than another, and therefore if a reaction would go. Well, this activity table happens to be based upon a standard reduction potential table. So what we're looking at is standard signal displacement, which is A plus B x plus gives A y A y plus B, which means that the A is becoming a cation, and the B, which is a cation, is becoming a solid. Now, this only happens if A is more active than B. So let's see how we can translate that into reduction potential terms. So the standard single displacement is actually two half reactions. It's A going to AY plus and BX plus going to B. You'll notice that the A going to AY plus is an oxidation. And the reason we know that is because A has no charge. And then A has charge of Y here, or Y plus, which means that it's gone up in charge. Conversely, the B, which is X plus, becomes a B, which means it's going down in charge. So that is a reduction. So we've got an oxidation, we've got a reduction. This will be spontaneous if the E naught cell value is going to be positive. And I'll show you an example of that. So we can use the reduction potential tables here to determine if this reaction, zinc plus Fe2 plus, will actually proceed. So here's how it works. I go on to the reduction potential table. Let's see if I've got it here. I don't have it here. I've got to go get it. So I go into the reduction potential table. I look for a reaction that involves zinc. The only one that we have here is this one, where zinc 2 plus 2 electrons gives zinc. Now the thing is that zinc, solid zinc, is actually on the reactant side in the example that we're looking at, which means we have to flip that reaction. So we know that that's what's going to be oxidized is the zinc. So we have to take that reaction and flip it. That's why it becomes positive 0.763 volts. The other one is Fe2 plus, and the Fe2 plus is going to be oxidized into iron. I think that is the only reaction that involves Fe2 plus as well. Get rid of that. So if we look for the Fe2 plus, and you can see it's up here. So there's only one reaction that involves Fe2 plus, and that gives iron there. And that's going to be negative 0.440 volts. That remains a reduction process. And I'm just waiting for this to go away. Okay. So what happens here is that we've got our E naught values because I had to flip the zinc one. So the zinc solid was on the reactant side. And that gave me positive 0.763 volts. And then I have minus 0.440 volts for the iron. And then when I add these together, I get a positive value. So what that would tell me is that if I put zinc in an Fe2 plus solution, zinc solid, and Fe, I should get a reaction because the E naught cell is a positive value. Here's another example. Let's say we tried to put silver in an Fe2 plus solution. What would happen then? Well, if we look at the silver reaction, again, we can find that on the standard reduction potential table. And the silver reactions up here, Ag plus an electron gives silver, that's positive 0.800 volts. Now, again, that one has to be flipped around so that the silver ends up on the reactant side, and that becomes negative 0.800 volts. We find the same ion reaction as we did earlier, and you can see that the E0 cell comes out to be negative 1.240. So what that tells me is that if I put silver solid into an Fe2 plus solution, then I shouldn't get a reaction. It would just sit there and look at me. It wouldn't do anything. Yeah, so that's the upshot of all of that. I just wanted to give you that as an example. It will be applied later when we're looking at galvanic cells, and I'm doing these problems that I call direction of flow problems. And this is going to be an important concept that will rule what happens in those kinds of situations as well. So electrochemical stoichiometry, right? So what we're looking at here is the process essentially of electroplating. Now, in this instance, what happens is that we have a battery here that's actually going to supply power. We're actually not using two separate electrodes to produce a current. We're actually producing a current from a battery. And in this situation, we have a silver bar, and it's in a silver plus solution. And then we have a spoon here. The spoon is iron. And what we're trying to do here is plate this spoon, which is iron, with silver plus, which turns into silver. Now, how's that happening? Well, we've got electrons being supplied into the spoon. Ag plus in the solution gets turned into silver solid on the spoon. This is the process of electroplating. And whenever an Ag plus leaves the solution and becomes silver, then the silver bar here turns into Ag plus. So what will happen is this will end up dissolving a bit, the silver bar, and that silver will end up on the spoon. That's the basis of it. Now, because the process is not a spontaneous one for silver reacting with Fe2 plus, we know that we're going to need to provide power to the spoon in order to make this reaction work. It's not a spontaneous process. We showed that earlier. But if we have the right data, we can figure out exactly how much metal will be deposited on the spoon. And for that, what we need is we need the time that the current runs, and we need the current in the actual from the actual battery. So let's say that we have 1.00 hours and we supply 1.50 amps from the battery. The reaction, and you'd be given this as well, is the reaction of Ag plus with one electron to give silver. The first thing you need to be aware of is that current, which is in this case 1.50 amps, is going to be charged over time. Now, the charge is measured in a unit called coulombs, and charge has a relationship to electrons and the charge in electrons as well. And you'll see that link in a minute. But the other way to express current as well as amps is in coulombs per second. So coulombs is the standard unit for measurement of charge. That's what we're looking at. The Faraday constant, we've talked about the Faraday constant before, is defined by this relationship. 1 mole of electrons is 96485 coulombs. So that's the relationship that we're going to make use of during this process here. So 96485 coulombs in 1 mole of electrons. That's the total charge of 1 mole of electrons. So how do we get to something that's useful to us? Well, what we do is we do a little bit of dimensional analysis. We know that 1.50 coulombs per second, because that's an amp here, coulombs per second. And what we can do is we can take the hours and convert that into seconds as well. So 1 hour is 3,600 seconds. So if I stop the dimensional analysis right here where I've got the cursor, you can see my cursor, correct? Yes, okay, good. Then I would end up with coulombs. Now, if I take the Faraday constant here, I know 1 mole of electrons is 96485 coulombs, then I can convert those coulombs into moles of electrons. So that would be the next step there. Once I have moles of electrons, then I can figure out how many moles of silver I could expect to get. I get 1 mole of silver solid for every 1 mole of electrons that is transferred. And then I can multiply that by the 107.87. That's the atomic weight of silver directly off the periodic table. And that would tell me that if I used this current over this time, 1.50 amps, and for 1.00 hours, I'd be able to deposit 6.03 grams of silver onto the spoon. So that's how it works. So it's all dimensional analysis across here, not particularly difficult. Let me show you some resources I have here for this. It's in the Electrochemical Stoichiometry or Stoichiometric Electrochemistry folder. And I've got a worksheet for this along with answers. So I'll just do an example from here just to show you the setup again. Not incredibly difficult. Let me see where my pen is. Okay. So I'll do number 5 down here. Now this has answers. Oh, you can see the answers are already here. It doesn't have the working, but I'll show you the work. It's all the same pretty much. But if you've got, see, 2.50 amps, that's 2.50 coulombs per second. And we got 2.50 hours. So I take the 2.50 hours and I convert that into seconds to cancel out the seconds. So I know it's 3,600 seconds per hour. That's 60 times 60 to give 3,600 per hour. If I stopped right here, I'd have coulombs. I know that the relationship is that there's 1 mole of electrons for 96485 coulombs. These are figures I give you actually in the problem on the test, so you don't have to memorize that. And continuing on with the dimensional analysis here, I need to convert those moles of electrons into solid. Now you can see that 4 moles of electrons, you can see that from here, from the reaction that you're given, will produce 1 mole of solid. So that's important as well. So the 4 moles of electron goes on the bottom to cancel the moles of electrons that are on top here. So if I put this on the bottom, you can see that'll cancel. 1 mole of tin goes on top. And then I multiply that by the molecular weight, I shouldn't say molecular weight, I should say atomic weight of tin over 1 mole of tin. And that will give me my answer, which should come out to be 6.92 grams. Obviously, you get that atomic weight off the periodic table. The number of sig figs is going to be determined by what you're given here. And in fact, in you're looking at this example here, I've used the wrong number of sig figs. It really should be 3.0 grams, not 3.02, because the 0.50 hours only has 2 significant figures. So that's something to look out for, is the number of sig figs you've got here and here at the current and the time, and that will determine how many sig figs you have in your answer, which in number 5 would be 3.
I thought you were doing number 5, not number 4.
I know I'm doing number 5. I'm telling you, I was just saying about number 4 is that I used the wrong number of sig figs in the answer. That was my point, that's all. But no, you're right, I'm not doing number 4. All right, any questions? Let me close these blinds here. All right. So let's take a look at the test question and how that relates here. So, and you can see what I give you as well. So what I do give you is the Faraday constant here. And it looks as though, yes, you'd have to know about the relationship between amps and coulombs per second in order to get this right. Now, the X here is we don't know what it is. It's some sort of hypothetical element. It comes up with this molecular weight, and that's what you'll use at the end. So you don't even have to look it up on the periodic table. But this is done in exactly the same way. In this case, the relationship would be 3 moles of electrons for 1 mole of solid. And that's what you'd put into the equation there. All right, does anybody have any questions? All right. I'm going to go back here to balancing of redox reactions. Now, we've already done a little bit of this when we talked about the non-standard cells, and we got the total reaction for that from the half reactions that were in the table. We actually did do some balancing there in order to make those reactions add up. So there's a process, a whole process that we can use if we don't have balanced redox reactions where we can balance them. All right, so let's see what we do here. These are the steps that we have to follow. We've got to, first of all, split a reaction into half reactions. It's not difficult. You'll see how to do it in a second. We balance the atoms that aren't hydrogen or oxygen. These are typically the ones that are being oxidized or reduced. The next step, we add water to balance the oxygen. Then we add H+ to balance the H. We balance the charge by adding electrons. And then we multiply the half reactions to make the electrons the same. Then we add the reactions together, cancel the electrons, and then balance this for base. So let's see how this process works. So I'll do it out step by step as I've got it here. So here's our reaction that we're trying to balance. We've got Mn2+ going to MnO2. This is what I mean by splitting it into half reactions. Let me put it more in the middle of the page. Here we go. And then we've got Cr2O72- going to Cr3+. And what I would want you to see from this is that, now this is not something you have to do to balance this, but what I want you to look at is just the charges on each of these species. So you can see for Mn2+, it's pretty obvious what the charge is. It's +2 or 2+. In the case of MnO2, the charge is actually +4. Now, how do I know that? Well, oxygen has a charge of -2, and there's 2 of them. So that becomes -4. And that's how I know that Mn is +4. Now, my point here is that the charge on Mn is going up. It's going from +2 to +4. That means that this must be an oxidation. If this is an oxidation, then this must be a reduction. So let's see if we can work out what the charge here on chromium is. In the product, it's +3. In the reactant here, it's +6. The way I know this is that it's 2 times Cr plus -14, and all of this has to add up to -2, which is the charge on the entire species here. And you can see that Cr then would be 6. My point here is that the charge is going down. We're going from +6 to +3. That's a reduction. in all of these processes, what's going to happen is something's going to be oxidized and something's going to be reduced. So what I'll do now is I'll just delete all that and start it again, because I want a clean slate here so that I can get this going. Put this on the bottom. All right. So again, I'll set this up on top. Mn2 plus is going to MnO2. The other clue is that there's no oxygen on the reactant side. There's oxygen on the product side. So you know that we've added oxygens. I mean, that's pure oxidation right there. And you'll see in the other example, we're losing oxygen, and that's another sign of reduction as well. Okay, step one, we have sorted this out into half reactions. Does anybody have any questions so far about putting in half reactions? The next thing we want to do is balance anything that isn't hydrogen or oxygen. That means we're balancing the things that are actually being oxidized or reduced, which in this case is the manganese and the chromium. In the top reaction, we can see that we've got manganese and Mn. There's only one of them here. The charge is 2+, but there's only one. And then it goes to MnO2, where there's only one manganese there as well. So what we know from that is that is balanced for manganese. We've got one manganese, one manganese. Now for chromium, we've got two chromiums on this side, on the reactant side, and one chromium on the product side. So I'm going to put a 2 in front of Cr3+ to balance that out. And I have to, the way I do this, I have to do it as a coefficient, just like I would in any regular balancing process. So that's step 2. Anybody have any questions so far? Step 3 is we have to balance the oxygens, and the way that we're doing that is we add water to balance the oxygens out. Now the way that works is that on the top here, there are no oxygens on the reactant side, and there's 2 oxygens on the product side. So I need to put 2 H2O on this side to balance out the oxygens. And on the other one, we've got 7 oxygens versus 0. So I added 7 waters to the other side. I'm going to stop there for a second. Does anybody have any questions about how I'm balancing the oxygen by adding water? The next thing we need to do is balance the hydrogens, and we do that by adding H+. Because we're balancing for acidic conditions first here. On the reactant side, we've got 4 hydrogens, that's 2 H2Os. So that becomes 4H+ on the product side. On the other reaction with the chromium, we've got 14 H's on the product side, so we need 14H+ on the reactant side. So that's 7H2O, that's 14 H's. Does anybody have any questions so far? All right, the next step, this is probably the hardest step, is to add the electrons to each of these reactions. Now, in order to do that, we have to figure out what the total charge is on each side of each reaction. In the case of the first reaction, the total charge is going to be 2 on the reactant side. H2O, because it doesn't have a superscript here, doesn't have a charge. So no superscript, no charge. Mn2+ does have a charge, so that's 2. In the other case, we have 4 has been the total charge. So we've got 2+ going to 4+. And that should look familiar. We looked at that earlier. So we've got 2 going to 4 here. Now I need to figure out how many electrons. So what I like to do is I like to take the absolute value of the difference between them, figure out the difference in the charge. You can see it's going to be 2. And then what I do is I add electrons to the side with the higher charge. Now, why do I do that? That's because electrons are negatively charged, right? So since the difference between those is 2, I'm going to add 2 electrons over here. All right, I'll stop there for a second. Does anybody have any questions about adding electrons? All right, just for kicks, I want you to try this. I want you to figure out what the total charge is on the bottom reaction on the reactant side and what the total charge is on the product side, and see if you can figure out how many electrons need to be added and which side those electrons need to be on. So I'll give you a second to work that out. All right, so looking at the reactant side first, the total charge on this side is going to be 14 minus 2, which is 12. Then on the other side, we've got 2 times 3 plus, which is going to be 6. Remember, the water doesn't have a charge. The difference between the two, 12 minus 6, is going to be 6. So we need to add 6 electrons. We add the 6 electrons to the side with the higher charge, which is 12. 6 electrons goes over here. Now you'll always notice that the electrons will always be on the opposite sides of the 2 reactions. If you're getting a case where the electrons are on the same side, like the product side or the reactant side of both reactions, it means you've done something wrong. Does anybody have any questions about the 6 there or how I get that? Okay. The next step, once we've added the electrons, is we need to balance the 2 reactions by getting rid of the electrons. And so what we're going to do is multiply these reactions in order to get those electrons equal. You'll notice we have 6 on the bottom and we have 2 on the top. What that means is I'm going to have to take the top one and multiply it by 3. Now I'm actually going to show you how that works out here. I wouldn't usually do this because I think it's, well, anyway, you'll see. But that would be 6. You don't usually have to do this. Write it out. You can just leave it up there and then add them together in the next step. But I'm going to do this. It's 3Mn2 plus. It's 3MnO2 and 16H plus. No, not 16, 12. And then that'll be 6 electrons there. And then we'll have the bottom one, which I haven't changed. I've effectively multiplied by 1, really. The idea was to make sure I get those electrons equal. All right, so I'm just rewriting that reaction. So now you can see we're going to add these reactions together to get our full reaction. So the electrons are going to cancel. Now the hardest ones to work out here, now you notice also I try to keep the arrows in a nice little row as well. Put them all underneath each other, that helps. The hardest ones to work with here are the water and the H+. And the reason for that is because we have water in both on both sides here, and we have H+ on both sides as well of both reactions. Now if we look at the water first, we've got 6 waters on the left, we have 7 waters on the right. That means we've got 1 water on the right. Now, how do I work that out? Effectively, what I did was I subtracted 6 waters from both sides. It's just an algebraic situation right now. We've got like terms, so we're cancelling the like terms. For the H+, we've got 14 on the left, 12 on the right. That becomes 2H+ on the right. Okay, I'll stop there for a second. Does anybody have any questions? Then I just pull down everything else because they only appear once. We've got 3Mn2+, and we've got Cr2O72-. And then on the other side, we'll have 3MnO2s and 2Cr3+. And what I would say about that is that it's balanced for acidic conditions. Or balanced for H+. Now we can also make sure that we're right here, and this is one of the benefits of a redox question, is that at the end you can always check your answer and see if you did get the right response, because everything will balance, including the charges. So let's take a look first of all at the manganese. We'll just go through each individual element. We've got 3 manganese on the side, on the left, and then we've got 3 Mns on the right, so those are balanced. Chromiums, we've got 2 chromiums on the left, 2 chromiums on the right, that's balanced. Oxygens, we've got 7 oxygens on the left, and on the right we've got 1 oxygen here in the water. That's 1 plus 3 times 2 is 1 plus 6 is 7, so 7 oxygens, that matches as well. Hydrogens, we've got 2 hydrogens on the left, we've got 2 hydrogens on the right. Charges, I'll write the charges underneath here so you can see. So it's 3Mn2+, that's 6. We've got -2 and we've got +2. So -2 for dichromate, 2H+, that's +2. Total charge here is going to be 6 on the left side. On the right side, we've got 0 for the water, 0 for the MnO2. 2 times 3 is 6. Total is 6 on this side as well. So the charges match on each side as well. So you know that as long as all the elements match and all the charges match, then the thing must be balanced. So that's real. And if you're not getting that, and if it's not balancing, then it means you've made a mistake. You need to go back and find out where you've messed up. All right, does anybody have any questions? So the last thing we need to be able to do is balance this for basic conditions. So that, as I said, that's balanced for acidic conditions. And to balance it for basic conditions, that means we're using OH minus. We actually use the H+ one we just did as our basis here. Now adding or changing it to base is kind of like doing a titration, which means that we need to add enough OH minus to balance out the H+ on each side. So what I do is I add 2 OH minuses to both sides. Now, if I do that, then the two H pluses and the two OH minuses react together. And what that will do is it will form water. So it'll be 3Mn2 plus Cr2O72 minus plus 2H2O gives H2O plus 3MnO2 plus 2Cr3 plus 2OH minus, the OH minus we added. Now the last thing we can do there is cancel out the water, so we subtract one water from each side, and we would be left with our final reaction that's balanced for base. Which will be 3Mn2 plus Cr2O72 minus plus H2O gives 3MnO2 plus 2Cr3 plus 2OH minus, and that will be balanced for basic conditions. And if I went through and checked the balancing on that, I'd find that that worked out as well. So we've got the acidic conditions up here and the basic conditions down here. All right, does anybody have any questions about any of this so far? All right, as far as resources go, well, you do have the old tests. The old tests have good examples of these, and you've got the keys for those as well, so they're not bad. I'm actually going to do a couple of examples from the test you'll be doing. So let's see what those look like. So they look a little bit nastier because I don't use real elements, I use X's and Y's. So it's X and Y that are being oxidized and reduced here. I'm going to do an example here. And what we're looking for here is the sum of the coefficients. So I'll show you what that looks like. If you weren't sure about how to proceed with this, I do have a video that shows you how to handle question 9. Okay, so let's see how we would go about it. For this one, we would do XO2 minus is going to X2 minus, so that's one half reaction. The other half reaction is Y2 goes to YO2 3 minus. Any questions so far about half reactions? The next step is we need to make sure that the X's and Y's are balanced. In the top reaction, we've got one X on the left, one X on the right. On the bottom reaction, we've got 2 Y's on the left and 1 Y on the right. So I need to put a 2 in front of here. If you're going to forget a step, that's generally the step that people forget. It's making sure they balance the X's and Y's. Does anybody have any questions so far? All right, for both reactions, I'm going to leave this in your hands for a second. For both reactions, I want you to figure out how many waters you need to add to each side to balance out the oxygens. So on the top reaction, how many H2Os do you add? On the bottom reaction, how many H2Os do you add? So on the top, we have 2 oxygens on the left and 0 oxygens on the right. We would add 2 waters to the right side. On the bottom reaction, we've got 0 oxygens on the left and 4 oxygens on the right. That would mean we'd add 4 H2O. on the bottom one. It's 2 times 2 to get the 4 there. I think that's another common mistake, is not realizing that you have to multiply by 2. Any questions? On the top reaction, we've got 2H2O. That means we've got 4 hydrogens, so we add 4H plus. And on the bottom reaction, we've got 8 hydrogens, which means we add 8H plus. So we balance the hydrogens by adding H plus. Any questions so far? All right, I'm going to leave it there for a second. I want you to figure out how many electrons you're going to need to add. Now remember, to do that, what you'll need to do is figure out the charges on each side of each reaction, take the difference, and then add electrons to the side with the higher charge. I'll say that again. Find the total charge on the right side and the left side. Find the difference and add electrons to the side with the higher charge. On the top reaction, the total charge is going to be 4 minus 1, which is going to be 3, going to negative 2, well, negative 2 plus 0 essentially. So it's 3 going to negative 2. The difference, 3 minus negative 2, is 5. A common mistake that people will make here is they'll say 3 and negative 2, the difference is 1, but it's not, it's 5. So it's 3 minus negative 2, which is 5. The 5 electrons get added to the side with the higher charge, which is the 3 side. So the 5 electrons go over here. I can leave myself quite enough room now. Let me move everything over a little bit. I can do that. There we go. Okay, I'll stop there for a second. Does anybody have any questions about where the 5 is coming from? On the bottom one, the charge is 0 on the left, and it is, let's see, so it's negative 6 plus 8, which is positive 2. Now the negative 6 comes from 2 times negative 3, and then you've got the 8 here, negative 6 plus 8, the 8H plus. And that would mean the difference there is 2 minus 0, which is 2. So we're adding 2 electrons to the side with the higher charge, which is the right side in this case. There we go. Does anybody have any questions so far? And the next thing we do is we want to balance out the electrons. So we do that by multiplying the top reaction by 2 and the bottom reaction by 5. This will give us a common number of electrons, which is going to be 10 on the top and 10 on the bottom. So you want to multiply by the smallest numbers possible in order to obtain. It's kind of like adding fractions when you're looking for a lowest common denominator. You're looking for a lowest common factor here in order to make this work out. So looking at we'll do the H pluses first. On the top, I've got 2 times 4 is 8 H pluses. And on the bottom, I've got 5 times 8, which is 40. So again, 8 and 40, which means that we have 32 H pluses on the right side. So again, how I got that, 2 times 4 is 8 on the top. 5 times 8 is 40 on the bottom. 40 minus 8 is 32. That's how I know I've got 32 here. Does anybody have any questions about 32H plus? Now, as for the water, I've got, let's see, 2 times 2 is 4 on the right side. And on the left, I've got 20. So that would be, is that right?
Yeah, you got 20 on the left side.
And 4,
HCl.
yeah, so 16, right? Yeah, 16, that's good. Just double checking that. Okay, so 16, that seems to make sense. And then we bring everything else down. So that would be 2 XO, 2 minus. Remember, we are multiplying by 2. And on the bottom there, 5 Y2s. And on the other side, the right side, we've got, let's see, 2x2 minus, and then a 10 YO2 3 minus. And that should be balanced. And it just says to balance it for acidic conditions. You don't have to balance it for basic conditions because that's not what it's asked for. But it would be, let's see if it does actually work out here. So number of X's, we've got 2 on the left, 2 on the right, so that's okay. Y's, we've got 5 times 2 is 10 on the left and 10 on the right, so that's okay. Oxygens, we've got 4 plus 16 is 20 on the left. On the right, we've got 10 times 2 is 20, so oxygens are okay. Charges, we've got -2 plus 0 plus 0. So -2 on the left. On the right side, we've got 32 plus -4, 2 times -2, plus 10 times -3, which is -30, which adds up to -2. So the total charges work. Now the question is asking for the sum of coefficients. So unless you balance this correctly, the sum of coefficients won't work out. But the sum of coefficients is going to equal 2 plus 5 plus 16 plus 32 plus 2 plus 10. So it's just all the numbers added up in front. And if it turned out that one of these didn't have a number in front, you'd assume it was a 1, just like you would for a regular reaction. But in this case, it would be 2 plus 5 is 7, plus 16 is 23, plus 32 is 55, plus 2 is 57, plus 10 is 67. So the answer would be 67. Again, you won't get 67 unless you balance it correctly. So there's really no way out of it. Does anybody have any questions? I'm going to re-roll or pull up another one, but I want to make sure it's a little bit different from the one we just did. So have a little bit of patience here for a second while I make sure I get one that will be a little bit different. I might have to do this a couple of times, we'll see. Might get lucky as well. No, I didn't get lucky. No, still didn't get lucky. I'll give this 2 more times, and if I can't get it, then I'll have to make something up. Still not. Maybe the 5th time's the charm, we'll see. There we go. Aha, yes, we got lucky this time. It's good. Okay. All right, so again, doing the half reactions, we've got XO 1 plus gives X2 1 plus, and QH8O gives QH6O2. So the things being oxidized and reduced here are the X and the Q, and I'm pretty sure it's the X that's being reduced because we're losing oxygen, and the Q is being oxidized because we're gaining oxygen. So that's a good little check, because then you can figure out if you've got the electrons on the correct sides as well. So looking at the first thing we need to do, balance the X's, balance the Q's. The Q's are okay. We've got 1 Q on each side. The X's, though, we needed 2 in front of the X on the right side. Any questions so far? Next, we balance for oxygens by adding water. I'll do the top one, which is going to be 2H2O, because there's 2 oxygens on the left side. Now there's 2 oxygens on the right when we add 2 waters. I want you to do the oxygens on the bottom one. So how many waters do you need to add to balance the oxygens on the bottom reaction?
1.
On which side is it going to go on, Kyle? Yeah.
The reactant side, the left side.
All right. The reason for that is because we had 1 oxygen on the left and 2 on the right, which means we need 1 oxygen more on the left in order to make it balance out to 2.
Sure.
The next thing, we need to balance the hydrogen. So we have 4 on top, 4H plus. And on the bottom one, this one's a little bit more difficult. All right, how many H's do we need to add? H pluses do we need to add? And which side do they need to go on?
For right side.
4 on the right side. Okay, so we've got 2 plus 8 is 10 on the left. We've got 6 on the right. The difference is 4. So now we need 4 H pluses. So now we've got a total of 10 hydrogens on each side. All right, the next thing we need to do is balance the electrons. Okay, so I'll have you all do that. how many electrons did you get on the top, folks? Alex, are you there?
Yeah.
I got 5 on the left.
Okay, 5 is correct. And on the bottom one, it should be 4.
4.
Yep.
Okay. How do we get 5 here? We got 4 plus 2 is 6. So on the, so this is for the top, I'll go ahead and do this. Top, we got 6. 4 plus 2 is 6. And that goes to 1. So the difference there is 5. We add 5 onto the left side. For the bottom one, we've got 0 going to 4. So the difference there is 4. So we have 4 electrons to the right side of the bottom one. Okay, after that, we multiply the top one by 4. We multiply the bottom one by 5. Has to give us equal numbers of electrons. That's the smallest numbers that we can use there in order to make that happen. We'll do the H pluses first. And on the H pluses, we've got 4 times 4 is 16 on the left, and on the right, we've got 20, 5 times 4. So the difference there is going to be 4. For the waters, we've got 4 times 2 is 8 on the top and 5 on the bottom. Sorry, 5 on the bottom. Yeah, so 8 and 5, so 3H2O is what I'm getting there for the waters. Okay, take a look at the H pluses and the H2Os. See if you agree with me.
No.
Kyle, you don't?
Isn't it the H2O on the right?
Yeah. Yeah, because that would be 8. And yes, that's right.
Yeah.
Yes, you're right. So the H2O goes on the right. The H plus is on the correct side, right?
I agree with that, yes.
Yeah, okay. Yeah, so the water's on the wrong side, you're right. Okay, the next thing we need to do is put in our other bits and pieces. We've got 8 XO1 plus, and on the bottom we'll have 5 QH8Os. And on the other side, we'll have 5 Q H6O2 and 4X21 plus. So the sum of coefficients then would be, let's see, 8 plus 5 plus 4 plus 3 plus 5 plus 4. So 13, 17, 20, 29. What you should get there. All right. Does anybody have any questions? So let's see. You got the practice test. I think obviously the practice test is probably the best thing to do to practice these, because these are the problems you're going to see on the real test. So I think it makes sense to practice as many of these as you possibly can. And we've gone through both possible types that you can see. The other thing, let's see what else we can do here. In the redox equations reactions folder, I've got some redox problems on a sheet here as well. Along with their answers, so you've got a worksheet there you can look at. And then there's some more as well here too. And then you've got your fun quizzes as well. So those for practice as well. All right. Does anybody have any questions about these redox? All right. Well, I guess we'll leave it there for today then. And I won't catch you on Tuesday. There is no school on Tuesday, so don't come to class on Tuesday. I'll see you all next week, next Thursday.
Sounds great, Professor. Thank you.
All right, no worries. Thanks for coming and not leaving me by myself.
No worries. Have a good.
Appreciate it. All right, I'll see you guys later.